In this video, we're going to talk about the equilibrium constant. Specifically, we're going to talk about how to interpret the magnitude of the equilibrium constant. So to recap, the equilibrium constant, or K, expresses the ratio of product concentrations to reactant concentrations at equilibrium. So we look at products over reactants at equilibrium, which is when the rate of the forward reaction equals the rate of the reverse reaction. And the magnitude of K indicates the extent to which a reaction proceeds. Now, if K is much greater than 1, meaning 1,000 or more, the reaction proceeds nearly to completion. So at equilibrium, the system contains mostly products with very few reactants. If K is greater than 1, that means the products are favored. You'll have more products at equilibrium. So the reverse is true. If K is less than 1, reactants are favored at equilibrium. If K is much, much less than 1, meaning 0.001 or smaller, the reaction barely proceeds, meaning very little product is formed, and you're going to have a lot of reactant left over. Okay, so if you have very large K values, that indicates a very strong product formation. Small K values suggest that the reactants remain largely unchanged or are largely reacted. Understanding K helps predict the reaction behavior and equilibrium composition. So we're going to look at a couple of examples. Let's start with this one. It says, given the following reaction and equilibrium constant, determine the relative amounts of reactants and products at equilibrium and explain your reasoning. Okay, so we have a reaction here, and we have a K value. So if you look at the K value, it's times 10 to the 7, which is much greater than 1,000. So because it's very large, almost all of the reactants are going to convert to products. At equilibrium, there's going to be very little A and B left, with C and D dominating the system. Here's another example. So it says, given the dissociation constants for the following weak acids, determine which acid is weaker and then justify your answer. Okay, so we have two values. They're similar. They're both times 10 to the negative 4. However, the bottom one is a little bit bigger of a number. So since the stronger acid disassociates more, the acid with the larger K value, or HNO2, is stronger. HF is going to be our weaker acid because it has a lower dissociation constant, just by a little bit. Okay, here's another reaction. It says, given the following reaction and equilibrium constant, determine the relative concentrations of reactants and products at equilibrium. Okay, so here K is very small. It's times 10 to the negative 4. So that means the reactants are going to be favored. At equilibrium, there's going to be significantly more A and B compared to C. And here's our last example. It says, given the precipitation reactions and their equilibrium constants, determine the extent to which precipitation occurs in each case. So a large K value, remember, anything over 1,000, so like this top one right here, it's times 10 to the 11th, means nearly all of our silver and chlorine ions are going to precipitate as silver chloride. A very small K value, such as the case in their second reaction here, means that only a small amount of A and B are going to form our solid AB. And that's really all there is to it.